And now we are going to prove the statement that x plus y is equal to y plus x. And this is going to be our theorem. And this is commonly called as the commutative law of addition. And the intuition behind it is that let's say we assume x to be 2 and y to be 3. It is easier to see that if we decompose it into, we can also write it as 3 plus 2, and then again it will be the same in both ways, right? And so we can see that RHS here is again equal to LHS. Right hand side is again equal to the left hand side, but this is not the proof, right? This is only the intuitive explanation of it. But let's prove it. We are again going to prove it using induction. So, but before I go on to proving it, let me remind you again what the property of addition were. So the first property again was x plus 1 was equal to x prime. The second property of addition was x plus y prime was equal to x plus y whole prime. One more thing, two other properties we are going to use in order to prove this commutative law of addition. Then the properties were taken from the construction of addition. If you remember from the construction of theorem 4, we had that construction. We set the addition of two numbers to, first of all, we said that x plus y was equal to y prime for x equal to 1, and second of all we said that x prime plus y was equal to x plus y whole prime, right? When we proved the existence of theorem 4, the existence part of it, I'm again going to link it in here at the video. I'm going to link at the right side of the screen here. You can click it and then you can see the whole construction, and then you'd see that we in the middle of the video we set the addition to these two properties, and this is what we are going to use here now. Now to the first part again, we are going to prove that x plus y, or x is equal to 1. Here we're going to assume that, and then we're going to write 1 plus y was equal to, what is it equal to, right? What is it equal to? It equals to y prime. How can we write it like that? We can write it by using this construction here. And again, can we write it in such a way that y plus 1 is equal to y prime? I think we can, because if you follow that from here. So what we have here is here. What do we have here? We have here this. And so we have proved it for 1. We can say that x plus y is equal to y plus x when x is equal to 1, right? This is the first part of the induction. Now for the second part, what we are going to see. Now the second part is to show that x plus y was equal to y plus x, and this holds, right? This holds true, right? And so can I write it? And so what would that be? What would this be? Can I expand it? I can expand it in such a way as to write, I can directly write it using this part here. And again we are going to pull that trick. We are going to see that this part is actually equal to here, this here, right? So this part inside of it is actually true. We have assumed it, and so we can write it as such. Can we write it? I think we can, right? As we have already discussed, we are going to use this and we are going to convert this statement to this statement, right? And so again, can I write this? I think I can, because this follows directly from here. This is the second part of the addition. And what was the second part? The second part was that x plus y prime was equal to y plus x, sorry, x plus y whole prime, right? And this was our properties of addition. This was the second one, right? And this follows directly from it. So what we have done here, we have done this. We have expanded this to this, and we can see that both of these sides, they are equal to each other. And so we have proved that whenever for x plus y is equal to y plus x holds true for x, or x prime rather, whenever it is true for x. And so we have proved that x plus y is equal to y plus x is true for all natural numbers by axiom 5, which is our axiom of induction here, right? And hence it is proved it. And again, I want you to look at the proof again in its entirety. First, we prove this for the case of 1, and then we use these two properties, and then we prove this for the first case, and then for the second case. And hence we proved it for all natural numbers. And this completes our proof here.